free expansion through a valve. Welcome to another video of Learn with Vishran Masala. Today we'll be learning about free expansion through a valve. At this point, it may be profitable to consider the free expansion of a gas through a throttle valve, since its use was the first process to liquefy gas, and it still employed as at the present time. So it has always been called the Joule-Thomson expansion, named after the early pioneers of cryogenics. So Joule and Thomson, nice. Assuming an ideal gas, and if only internal external energies are considered, ignoring potential and kinetic, the effect of free expansion through a throttle valve may be analyzed as follows. No work is done, so work is 0, and no heat is exchanged, so Q is 0. Therefore, initial UV plus PV P1 V1 equal to U2 plus PV2, which is enthalpy equal to enthalpy 1 equal to enthalpy 2, which is the difference between the enthalpy is 0. So there is no change in enthalpy, as ideal gas cannot be cooled by a Joule-Thomson free expansion. Since there is no change in enthalpy, a Joule-Thomson expansion is called isenthalpic inversion. In a real gas, however, consideration has to be given to van der Waals equation of state P plus A divided by V square equal to B minus not equal to into B minus B equal to RT, which includes the involvement of the molecules in a gas. The molecules in a gas have been finite size, and their volume is represented in the formula by the letter B. The molecules also display an intermolecular force or attraction whose value is measured empirically in the formula by the letter A. In the Joule-Thomson effect 10, it was found that not all gases showed a cooling effect when expanded through a throttle valve. Certain gases, which as hydrogen and helium, showed a heating effect. They calculated an inversion point for all gases, which is now known as μ(Z)T). The point at which μ(Z)T is 0 is known as the Joule-Thomson inversion point. If van der Waals equation of state is applied to a free expansion of a real gas in order to determine whether or not a gas will be cooled or heated by free expansion, the following equation is useful. Nice. So μ(Z)T equal to 2A divided by RT 1 minus B divided by V whole square bracket CP 1 minus this is the equation. You can look at it. The above equation may be simplified for a large value of specific volume to 1 by Cp to A divided by RT minus B. If T is lesser than 2A by BR, then UZ is positive and the gas will be cooled. If UZ is positive, the gas will be cooled. If the T is greater than 2A by B by R, then μZ is negative, the gas will be heated up. Okay, heated up. So the negative hunda chai heat huncha re, positive hunda cool huncha re. In general, those gases whose maximum inversion temperature is greater than ambient, say 290 Kelvin, will cool, whereas other gases like hydrogen, neon and helium will heat up. In summary, when a real gas undergoes a free expansion through a throttle valve. There is no external work and no heat exchange. It should normally behave as an ideal gas. There is subtle change, however, in the internal energy of the molecule of real gas as they disperse downstream of the valve. There is a minute increase in the potential energy of the molecules, which is more than offset by a decrease in the kinetic energy. The phenomena results in an overall decrease in the temperature, so however small, of expanded gas. Okay, so whenever this hydrogen and this gas is taken to that throttle, then the temperature is decreased. I got this from this. Okay, I don't know about you guys. Deviation from Boyle's law. From the figure 1.2 indicates a diagram for 1 kg of water at various isotherms and pressures. The dotted lines reunites the various points of the minimum PV and dotted diagram. So somewhat resembles a parabola. Within this dotted area, the air can, or for the matter any gas, is subjected. Okay, we can use this diagram to find some values in the numeric. We used to do that, what is this? Maximum inversion temperature for different gases. Let's see, for oxygen is 1761 Kelvin. So 761 minus 273. What is this? I am not quite sure. Let's go. To inversion and does not follow Boyle's law. Along the inversion curve, the Joule-Thomson coefficient is 0 because at the point on the inversion outline is 1 at which the slope of the isothermal line is 0. This indicates that outside of the inversion area, as gas flows, Boyle's law for hydrogen or helium, the inversion point is below room temperature. Table 1.2 indicates the minimum inversion temperature of various gases. It can be concluded from table 1.2 that most gases can be liquefied by free expansion through a throttle valve, with the expectation of helium, FO, hydrogen and neon. The latter gases have to be pre-cooled before being proceeded with free expansion. Each gas therefore requires an individual study of its inversion behavior and the value of the Joule-Thomson coefficient mu J(T). For hydrogen, it is necessary to pre-cool the gas to 198 Kelvin before any refrigeration can be achieved by the use of throttle valve expansion. In the case of helium, the pre-cool will have to reach up to 45. So some pre-cool should be done. Okay, I think let's learn out here, and adiabatic process will do tomorrow, right? Thank you for watching. See you in another video. Take care. Bye bye.